So if we're trying to find a particular solution for a linear differential equation, we've seen that undetermined coefficients sometimes works, but sometimes it doesn't work. So what could we do if it doesn't work? Since undetermined coefficients essentially comes down to making clever guesses for what a particular solution looks like, if undetermined coefficients doesn't work, we need to have some completely different way of coming up with a good guess. Now, as with undetermined coefficients, if you can't use undetermined coefficients, the first thing that you would probably do is find a fundamental set of solutions to the associated homogeneous equation. So let's just assume that we know, given this second order linear differential equation, let's just assume we know a fundamental set of solutions y1 and y2. So that means that the complementary solution, that is the general solution to the associated homogeneous equation, would look like c1 y1 plus c2 y2. And what determines these constants, c1 and c2, is any initial condition that you might have. But, the fact that these turn out to be constants is really sort of what makes this a solution to a homogeneous equation. Since the equation that we're dealing with isn't a homogeneous equation, maybe what we should think about is maybe these aren't constants. So maybe what we should guess for a particular solution is the same sort of thing, but instead of having constants multiplying y1 and y2, maybe we should have functions multiplying y1 and y2. Then it's really a matter of figuring out, well, if this is going to be true, what functions are they? So these unknown functions u1 and u2, we're going to have to figure out what they are. And if we can find appropriate functions, then maybe we can get a particular solution of this form. Now, as soon as we write this down, you can bet that we're going to have to plug this into the original differential equation. So to do that, let's take some derivatives. Also, just to save myself some writing, I'm not going to write this of x every time. So I'm just going to write u1 and u2, but keep in mind that u1 and u2 are functions of x, just like everything else, really. Okay, so let's take one derivative. We're going to have to use the product rules, so we get u1 prime y1 plus u1 y1 prime for the first piece. Then for the second piece, u2 prime y2 plus u2 y2 prime. Okay, and man, when we take a second derivative, each of these terms is going to require using the product rule, and so that's going to spit out 8 different terms, or I guess 6 since you can combine some of them, when we take a second derivative, and that's going to make things really, really messy. So that seems kind of unpleasant. But when we do plug this guess for y sub p into the differential equation, we're going to get one equation that tells us about one of the u's, but we have 2 u's. So we have 2 unknown functions here, u1 and u2, but we're only going to end up with one equation. It seems like we should be free to choose another equation, right? Usually, to solve a system of equations, you need the same number of equations as unknowns. We're only going to have one equation, but we have 2 unknowns, so we should be able to choose a second equation. Now, it takes some trial and error to see what is a sensible choice for a second equation, but one thing we might hope is to have some equation that makes this expression for y sub p prime simpler, so that when we take its derivative, we don't get quite such a mess. And it turns out that with a little trial and error, you can find that taking these 2 pieces and insisting that they be 0 is a good thing to assume. So we're going to assume that u1 prime y1 plus u2 prime y2 is actually equal to 0. So if you don't make this assumption, there are just too many possibilities for u1 and u2. Making an extra assumption sort of limits the possibilities so that you can actually find a function for u1 and a function for u2. So when we add this assumption, y sub p prime is much simpler. It's u1 y1 prime plus u2 y2 prime. Okay, now when we take a derivative, it's still messy, but it's not as messy. So second derivative is now u1 prime y1 prime plus u1 y1 double prime plus, and then for the second term, u2 prime y2 prime plus u2 y2 double prime. Okay, now we can plug all of this, plug our derivatives for y sub p into the original differential equation up here. So second derivative of y sub p is u sub 1 prime y sub 1 prime plus u sub 1 y sub 1 double prime plus u sub 2 prime y sub 2 prime plus u sub 2 y sub 2 double prime. Okay, plus, now the next term in the differential equation was our coefficient function p times y prime. So that's u sub 1 y sub 1 prime plus u sub 2 y sub 2 prime. And the third term was the coefficient function q times y itself. So plus q, oh, I left off my p over here. Okay, q times u1 y1 plus u2 y2. And this is all supposed to be equal to the right-hand side of the equation, which was f of x. All right, so boy, there is a lot of stuff here. Let's gather everything up according to the derivative of the u that it has. So we have some terms with u1 prime, so that's here. So u1 prime, y1 prime, and we have a term with u2 prime, that's right here. So plus u2 prime, y2 prime. All of the other terms have u's with no derivatives. So let's gather up all of the terms that have u1 with no derivative. So there's this one, that one. Since all of those have a factor of u1, I'm going to factor out this u1 out in front. So we get y1 double prime. From the second piece, we get plus, don't forget this coefficient function p, so p times y1 prime. Remember, we factored out the factor of u sub 1 here. Okay, plus, and then from the third piece, don't forget the q times y sub 1. Okay, now for the terms with a u sub 2 with no derivative, we have this one, and this one. So let's factor out the u sub 2 from all of those. We get y sub 2 double prime plus p times y sub 2 prime plus q times y sub 2. So just barely fits. Okay, so it looks at first like we haven't done ourselves any favors because this is still a huge mess, but remember, y sub 1 is a solution to the associated homogeneous equation, but that means that this sum here This is the left-hand side of the associated homogeneous equation, so this means it adds up to 0. That's what it means for y sub 1 to be a solution to the associated homogeneous equation. By the same token, the stuff in the second set of parentheses also adds up to 0. So what looked to be a huge mess at first actually comes out to be just u1 prime y1 prime plus u2 prime y2 prime equals f of x. And remember, so this is one equation that we get from plugging our guess for y sub p into the original differential equation. But remember, we made an additional assumption along the way, which was that y1 times u1 prime plus y2 u2 prime was equal to 0. Right? That was our additional assumption. So now we have a system of linear algebraic equations. We can use this system to find u1 prime and u2 prime. So this is just a little exercise in algebra. You can use elimination or you can use substitution, however you want to do it. I'll let you work through the algebra. I'll just write down the result. So what you get from solving this algebraically for u sub 1 prime and u sub 2 prime is you get u sub 1 prime turns out to be minus, let me make sure I get this right, minus y2 times f over y sub 1 times y sub 2 prime minus y sub 2 y sub 1 prime. And what you get for u sub 2 prime is y sub 1 times f over y sub 1 y sub 2 prime minus y sub 2 y sub 1 prime. Okay. Now these denominators actually, you might recognize these. First of all, they're the same. But second, y sub 1 y sub 2 prime minus y sub 2 y sub 1 prime, that's actually the determinant of y sub 1 y sub 2 y sub 1 prime y sub 2 prime. But that's the Wronskian. So u sub 1 prime is actually minus y sub 2 f over the Wronskian, and u sub 2 prime equals y sub 1 times f over the Wronskian. Okay, so we were able to find u1 prime and u2 prime. So at this point, we would integrate to find u1 and u2. So both of these would just be the integral of their respective formulas. Now, something to keep in mind about using these formulas to find u1 and u2 is that it matters which function you've labeled u1 and u2, right? The formula for u sub 1 prime has y sub 2 in the numerator, and the formula for u sub 2 prime has y sub 1 in the denominator, and also which function in your fundamental set of solutions, the y's, which you call y sub 1 and which you call y sub 2, affects the sign of the Wronskian. So if you interchange your 1's and 2's, then a bunch of minus signs shuffle around. It gives you the same result when you write down your particular solution, but it will change sort of how these formulas show up. So be careful to get everything in the right place. It's easy to lose a minus sign or to put a y2 where you wanted a y1, so just be careful. So in principle, right, if we start with this general situation, this general differential equation, y double prime plus p times y prime plus q times y equals f, in principle, we can find a particular solution just by finding a fundamental set of solutions for the associated homogeneous equation using these formulas, and then forming the particular solution u sub 1 y sub 1 plus u sub 2 y sub 2. Now I say in principle because in practice these integrals are often very, very difficult. But there are some examples where these integrals are things we can calculate, and in those cases we can actually find a particular solution to differential equations that we couldn't solve using undetermined coefficients.